Hello guys, welcome back. Today, the first day we have started discussing the problems on data science interviews and exciting stuff for data science and your preparation for data science jobs and quant, a lot of job related stuff. And also this is a different kind of approach. This will also include our sessions and exciting coding sessions, understanding pseudocodes and understanding the problem. So it will be an entire package of theory and applied. So I'm really excited today to share my thoughts with you, share my first problem and idea with you. And I'm not sure whether I've seen this problem, but this is a really famous problem which is asked in data science interviews, the probability interviews. At least it was asked in my to my batchmates in my final year in this job interviews, in quant job interviews and data science job interviews. So let's do this problem first. The question, the problem is simple. It tells that for a fair coin, what is the expected number of tosses to get heads in a row? Okay, that means 3 heads in a row. Now, if you have gone through the probability, okay, there's a disclaimer that you need to be very fluent in understanding the probability ideas and basic stuffs of probability to really understand what is going on in this lecture. If you have not, please revise and get back to this, okay? And I'm sure you will understand it. So the question asks you that for a fair coin, what is the expected number of toss to get 3 heads in a row? Now, if I ask you the same question, that what if 1 heads in a row? What will you tell? For 1 heads in a row, this question is equivalent to geometric distribution in probability. Okay, the first head, the probability of getting the first heads. And let's try to understand that. So you know the expected is, so if the P is the probability of success, then the expected number of to get the tosses is 1 by P. Okay, that is 2 if for a fair coin. But we will see this problem from a different angle. Okay, let's get started. So let's start. Let's say we are starting. Initially, we are starting. And let's say let's think about the first toss. The first toss can be heads, can be tails, right? Let's say it's heads or it tails with probability half and half. Now understand, so this geometric property, this idea of Bernoulli process being tossing ever, it's independent, right? It forgets what has happened in the past. So this is really memoryless property of this idea, this process, which really attracts this kind of beautiful symmetric properties and conditional stuff. Let's understand this. So first toss, let's say it's heads. Still, we have got a count of +1. This happens with probability half. And here also tells with a count of +1. I mean, a step, a number of the number of tosses has increased +1, right? For the first toss. So what we have got, let's say N1 be the number of tosses required, expected number of tosses to get the first head for 1 head. Okay, let's do it for 1 head. That's why the subscript 1 under N. So to 1 head, for if you want to get 1 head, then this satisfies it, right? So if heads is the corresponding outcome with probability half, so it is like this: for 1 step +1 with probability half into probability of heads. Say first toss is head. 1 step, we get 1 toss to need. We need 1 toss to get to the point. Okay, the number of tosses required to get 1 heads in a row. So we need 1 toss for that. But suppose we get tails. This is a tricky part over here. This is a beautiful part over the symmetric part, memoryless part, which tells you that if you get tails, you sort of go back to the initial position. If you get tails, you go back to the initial. You have gained 1 step, you have gained 1 toss, but you go back to the initial position and start over again, which is exactly N1, right? So it's like N1 plus M1s. So you're getting the total process takes N1 steps. So you're starting over again. So you get N1. But it happens with a certain probability, that is probability of tails. That is half. So let's see what happens. It's 1 into half plus 1 plus N1 into half. Lovely. Let's calculate it. So you get twice N1 is equal to N1 plus 2. So you get number of tosses is equal to 2. Exactly the same answer that we have got for geometric distribution, right? 1 by P. Very good. Lovely. Okay. But What about 2 tosses in a row? This is a trickier part. This is even trickier. Let's try to understand this. What if 2 tosses in a row? Let's try to get back and use the same steps. I will do it for 2 tosses. You do it for 3 tosses as a homework, as an exercise. Okay, it will enhance your understanding. So let's do the same. In the same idea, let's do it for, let's say, the starting point. So the first toss, we know that happens. But instead of first toss, we know that first toss के लिए we need n1 steps expected. First head. Now let's understand. First head का next toss देखो. Next first toss after first head. Okay. First toss after first head. If you see this, then it can be heads or it can be tails with same probability half. We know that. And each के लिए plus n1 steps. So plus 1 steps for here and plus n1 steps for here. Let me mark that. Here plus n1 plus. Right? Lovely. Now to understand this. And total takes n2 steps. If, let's say we are counting n2, this is the n2 wala stuff. If let's say you are counting n2, so n2 takes what? There are 2 cases. You get along this path or you get along this path, because the first head must occur. Then only you can tell this. Otherwise, it will not happen, right? If you don't get a first head, it will never happen. So it can only happen if you get the first head. So n2 is equal to what? First n1 steps plus 1 if you get heads, right? If you get heads, first head and this is the second head, the first toss after the first head give heads, that you get n1 plus 1 steps with probability half. That probability of heads in the first toss plus first head and first heads. First toss after first head turns out to be tails. So what do? You go back to the initial position again, the starting point. Not here, but here. So what do we get over here? We get n1 for the first one plus 1, but again it goes back to the beginning. To come back to the same place, you need n2, the actual number of steps, into probability half, right? So what do we get over here? We get that it's equal to, therefore it implies that twice n2 is equal to n1 twice n1 plus n2 plus 2. It turns out that n2 turns out to be twice n1 plus 2. Lovely. Twice n1 plus 2. So you know n1 is equal to 4, n1 equal to 2. Therefore, you get 6 over here. In fact, you can prove that for n tosses, it will turn out something to the power of 2 or something like that. It's a homework. For 3 tosses, you just do the same step. Okay. First double heads and then count that, because you know that for first double heads, you need n2. So come back again. So here it will be in that case n2, here n2 plus n1 plus n3. Just a small step, I will rub it off again, just so that you can do it yourself now. Lovely. So we have got 6 steps over here. Lovely. So we have got the solution. Now, if you're interested that if this doesn't seem very mathematical to you, then maybe you want to go into the depths of probability. So what is the theory going behind it? You must know this. Since you're a data science aspirant, you must know into the depths of the whole idea of probability, statistics, everything. The theory is called law of total expectation. You must, a book for good reading is Blitzstein. Blitzstein is a professor of Harvard, so you can read this book, or you can read Sheldon Ross' first course in probability. Both the books are good. There is a conditional expectation chapter. Go through it, you will find it exciting. You need to understand conditional probability first and then conditional expectation. Okay, lovely. So the mathematics behind it is called conditional expectation. I don't want to make it more theoretical. You will lose the interest, so I am keeping it right here. If you're interested, you can see other videos of mine explaining that. If there is not, I will surely make a video. Lovely. So what's after this? Let's try to go into the pseudocode and the coding perspective of it. It's really exciting. Let's understand this. So let's understand the pseudocode. So what we will do, we'll try to simulate this and see the mean. So how do we do that? How we can manage that? Suppose they ask you to do the R code or give the pseudocode in the interview. How can you do that? This is the idea. Understand, first you need to repeat this experiment for. So what do you need to do? First you need to repeat this. It's a bad color. First repeat. First make one experiment. First do one experiment. How to simulate this experiment? How? So what do you want to do? You want to understand, you want to run a for loop. Okay, you want to run a for loop. So understand this. You want to run, what do you need to do? You want to toss it again and again till you get the first heads. Okay, or rather the first two heads, consecutive two heads. So you need to keep on tossing Bernoulli. Keep on tossing. That is done like keep on tossing Bernoulli is done like while loop. While keep on tossing. What happens is that every single time under this, you toss a Bernoulli. Okay. And let's say initially you have tossed two Bernoulli over here. Those are saved. So toss a Bernoulli. If after that Bernoulli, the previous, that step and the previous step are both heads, then you stop the loop over there. Then you stop that over, stop the process. Stop the process. So you keep on tossing, toss a Bernoulli. You see, check whether the previous step and the previous step is heads and heads. If it is true, if it's true, if it's false, there are two cases. You stop or else continue tossing. This is the main idea. And every single step you need to count the number of required. So every single step you need to, there is no here, no ending line over here, ending not the ending the code. You need to count number of such loops before it stops. So let me write it down again and just make you understand again. What do you do? Let me make it much more enhanced and understandable now. First, toss two Bernoulli. Okay. Now start a while loop. While you keep on tossing. When now you toss the first, toss a coin, Bernoulli coin. Then you check whether the previous two are heads and heads. If it's true, you take one step. If it's false, you take another step. So how do you how do you codify this? How do you codify this? You have to understand this. So this is done by R binom in R. How do you toss a R binom function in R? I will be showing it right to you now. And while is done while, and toss a coin again, you do R binom. But the understand is that you have to keep on tracking this, that every count. So every time a while loop ends, you count is equal to count plus 1. So for this experiment at the end, when the experiment stops, this count variable will count the number of tosses required. Count variable will count the number of tosses required for every step. So now you repeat this experiment 1000 times and you get the average. By law of numbers, the average will go to the actual probability, will go to the actual number. Okay, and that is the actual expectation. It will be around 6. Okay, so first toss to boundary, and let's check that. Let's understand that how we do this over here. So let's go to RStudio now. So if you have seen the RStudio over here, let's see what we are doing. So first we are experimenting is equal to null. Like, what is the experiment? We will understand experiment is the actual experiment. I will tell you what is the experiment. Okay, we are taking the mean of the experiment. Experiment is a vector of all these counts for 1,000 such experiments, such trials, such experiments. Sorry. So you do this experiment 1,000 times and take the average. So vector of all this counts for thousands of experiments. So you prove it to took it to be null, okay, because you have not done an experiment. So now what you do is try is one experiment, try is one such experiment, okay. So try is a variable, it's one such experiment, and you are counting it 1 to 1,000 times. So this is like the for loop for. So I'm doing it for 2 consecutive heads. Okay, try to understand that for the experiments, Now inside each of these experiments, what you do? This is the main idea. Inside each of these experiments, you first set the toss sequence is equal to null. That is a sequence of toss in the first experiment, in the corresponding experiment. Then you do the first toss. There's R binom 1, 1, 1. This is the first toss. This is the second toss. Why I'm doing the first toss and second toss not inside the for loop, you will understand, because it's like a recurrence relation, okay, where you need to define the first step and second step, because you will understand, I will tell you. So this is the first initial. So you do the first toss and second toss. Okay, that's the first, you save it. Now you add these 2 tosses. This is the toss sequence is what? Toss sequence is the sequence of tosses. I should write it over here. A sequence of tosses. Yeah, sequence of tosses. Now you add, this is adding the, you're adding the tosses to this vector of tosses. That is the idea over here. Now I is equal to 2, you know I is equal to 2, initial number of tosses. Now what you do is that, is it the number of tosses? I is the number of tosses. Number of tosses. What do you do? You do the while loop, that if the number of tosses is greater than 0, which is always greater than 0, so it will continue till like always, okay, until we stop under certain condition. So this is the condition. If the toss sequence, that is a ith, so suppose at that moment of time, the toss sequence of I and I minus 1. So already 2 tosses has happened. So we start with that we start that suppose that among the 2 tosses, the first 2 are heads. We stop that at that moment. So C of I and I minus 1, the ith and the I minus 1. So at that point of time, I is 2. So in the first loop, what happens is if checks whether 1 and 2 is actually equal to true or not, like it's actually equal to 1, 1, there is heads or not. It actually checks that. If it's true, then we break this loop. Okay. If it's not true, it continues. So if it's not true, then it added a toss. So it's do another toss. So it checks the condition of heads and heads. Now what it does over here, now it breaks, if the condition is true, breaks the loop. If the condition is true, then what happens is that if the condition is false, then we toss again and add it to the loop. This is added to the sequence and add it to the sequence. Makes sense, a lot of sense. And we also increase the count number. We increase the count of the toss. Why? Because the toss sequence we have to choose the last and the pre-last, just the one before the last. So that's why that is done by I. So we need to increase. We need to keep a track of that. And again, we come back to the second loop. What happens? We again check that if the third toss and now I is equal to 3. Now third toss or second toss is equal to heads and heads or not. Then if it's not, then it continues and then it continues till it stops. Okay, so toss sequence count the number of such. So toss sequence counts the, not a toss sequence, but I counts the number of such tosses required. So when it the breaks, the I stores the number of such tosses required. So experiment, initially it was null, so we add I to that experiment, corresponding experiment. And then again we start the again experiment again from the beginning. For try is equal to 1 or 2. We do this again and again for 1,000 times. And we take the mean of all these experiments, which we expect to come out to around 6. So let's do that. Let's do that. For loop. Let's do that. So we have done all the experiments over here. Let's see the mean. It's coming to 6.047, which is around 6. Perfect. Lovely. Let's do this again. Let's do this again. 5.996. In fact, if we do this again and again and again, we can get a graph whose mean will be around 6. We can plot a histogram of this because it's a random variable after all here. So you can draw a histogram which will be around 6, mean around 6. Lovely, and variance will be really less. So we have got, again do that. 5.99, again do that. 6.0, it will be varying. So what is happening? We are getting around 6 and it matches. So your homework is to do it for H, and implement that here, okay? So I will give the code in the corresponding YouTube description and comment. Check that out. And if you like this, subscribe to this channel and share it to your friends who really need really need this video. And don't forget to like and subscribe to our channel. And thanks for your support. Thanks for your love. And do share it with your friends. Thank you so much. See you in the next video. Stay tuned and stay blessed.